Today we will see a problem, one-way slab. We'll do the structural analysis of one-way slab and see how to do this procedure when the ACI moment coefficients are not valid. Okay, so it's a one-way continuous slab. This is the floor plan, and you can see these beams running in this direct east-west direction, and this is the one-way slabs. You can say this one or that one. So all these are the one-way slabs. It's spanning in this direction, the shorter direction. So what we're going to do is we're going to see how to perform the structural analysis of the slab. So let's just familiarize ourselves with this plan. So these are the columns running, and there's a wall over here as well anyways. So there is this cantilever of 6 feet beyond the edge of the column. Okay, so we'll see how to analyze this, and this is the cross section of this is the cross section where you can see the slab in slab thickness, and you can see the beams cross section actually. So this is the cross section AA. Okay, so you can see this is 6 feet cantilever. Okay, this is the cantilever in the plan, and this is the cantilever in the section. Okay, so 6 feet from the edge of outer edge of the column, and center to center of these beams are, you can see over here, 14 feet. Okay, 5 spans at 14 feet, and this is total 70 feet. So these are center to center. You can see center to center, it is 14 feet. Center of the column to the center of the next column. Okay, and the beams are 1 feet 6 inch wide. Okay, and you can see that the center to center is 14 feet, but of course the edge to edge distance is 12 feet 6 inch. Okay, so for structural analysis, we need to, our model is a center line based model, so we used center to center distances. So the spans are 14 feet. So this is not the, so the spans are 14 feet, 5 spans, and then this is the cantilever, 6 feet outside, and it means half of this 1 feet and 6 inch, which is 9 inches, or 0.75 feet, will be from center of this column to the end of this slab. Okay, so this is actually a problem given in this concrete design handbook by ACI. Let me show you the first page. This is the first page of this. So I'm using this example, and I want to explain how to do the structural analysis. Of course, this handbook includes a solved problem, but of course it doesn't include the step-by-step procedure. Okay, so this is an example from one-way slabs. So let's begin. Now, since ACI coefficients are not applicable, because you can see a cantilever over here, and once this cantilever is, so there's no case in ACI coefficients where you can have a cantilever included. Okay, so even if, so in certain cases, the ACI coefficients may be applicable, may not be applicable, but the general structural analysis procedure is always something that you can do. So let's see, this is the, so I won't be covering the design part in this video. I'll just be covering the structural analysis part. The design procedures are pretty much well defined, and once you have the MU values, you can do the flexural design. Same goes for the shear design. So so this is slab thickness decision. We're not discussing this part. This is just related to the general. So we're working with it. So it's finally happens to be a 7-inch thick slab. The self weight of the slab is, you can calculate it using the density or the unit weight, 150 pound per foot cube, and you convert the 7 inches to feet. So this is also now in feet, and you get 87.5 pound per square foot. Okay, so the live loads for, let's assume it is for the areas it will be supported. The slab that will be supported will be an assembly area and corridor, and for the assembly areas and corridors for the in the ASC 7-10 table, you can see it is table 4-1, it is 100 PSF. So the live load is 100 pounds per square foot, and also to account for the weights of the ceilings, partitions, HVAC systems, etc. Additional 15 PSF dead load is also considered. Okay, so the dead loads are 87.5 PSF, the self-weight of the slab, and the 15 PSF for the additional for the HVAC and ceilings, etc. So this is the dead loads, 102.5 PSF. So these are the two load combinations for the gravity load resisting systems you should check. And of course, the second one, 1.2 dead plus 1.6 live governs in this case. So 123 PSF is affected dead load and 160 PSF is affected live load, and the total is 283 PSF, and this governs in this case. Okay. Now this is the part where most of the time has to be spent. You cannot simply apply this 283 PSF all over the spans and then just calculate your get your results. This is not the correct way of doing it. You have to consider the live load patterns. So we'll be using the ACI 318 approach for considering the pattern loading. So first, so the affected dead load is applied on all spans, and affected live load is applied in patterns for each critical moment. Okay, so we'll have to do the analysis separately for the dead loads, affected dead loads, 123 PSF, and then for the live loads, we will apply the live loads at locations which can maximize a certain moment at certain locations. So for different locations, we'll have to apply different patterns of live loads. So this is a general diagram given over here, but this is of course not clear to anybody who is not yet familiar with these procedures. We'll see these procedures in detail, but let me just take you a little bit through the solution process. The slab analysis, there are some general things that are discussed in 6.3, and then this analysis approach. So essentially they are saying that since it is not, the slab will not participate in a lateral load resisting system apart from working as a diaphragm, so we can do only the gravity load is something we need to consider for the slab. Okay, so this is the final output of the analysis as far as the bending moment is concerned. So this is in fact the moment envelope, and we will see how this is developed. Now, depending upon different approaches that you take, you can have slightly different values for these peaks, but essentially you need to understand the concept here. So, so let's see how we actually develop such moment envelopes using analysis, and we'll start from scratch. So this is just the commentary from on the same diagram, and this is the summary from the same moment envelope diagram. So, and then this similar things have been done for shear as well. You can do similar procedures for shear. So let's start with the analysis. So let's first model the slab, and then in any software, structural analysis software. So so there's one thing that you need to you might already know is that for slabs, we need to consider a unit width of the slab, and we do the analysis for unit width of the slab, and then all the quantities that are obtained are for that unit width of the slab. For example, when we end up with MU, that MU is for the will be in kip foot per foot width of the slab, unit width of the slab. So we'll using US customer system, so we'll take 1 foot width of the slab, and we'll then so it is essentially acting as a beam having 1 foot width. Okay? So our beam, you can take it as a beam having a unit width, 1 foot width. Okay? So we need to first develop that model over here. Now, this part is free. This is the cantilever portion, and then we'll have a beam supporting the slab, and then we have another beam, and so on. This continues until this edge beam. Now, we need to realize here that the first thing that you need to do is to develop a structural analysis model. Now, the analysis model that I'm going to follow, there can be different models that different people would recommend. ACI 318 does not give a specific procedure for this. It says that the procedure should be any procedure is valid as long as the equilibrium and compatibility conditions are met. So I'm going to use guidelines given in the book by James K. White, Reinforced Concrete Mechanics, and design. Okay, let me show you what is the first page of this book. So this is the title page. I just wanted to show you which book I'm using, and this is the let me take you back to the same part where I'm interested. Okay, so this is the procedure we're going to use. Okay, so this is related to structure. This is the article 5-2, and this is the sub-article structural analysis of continuous beams and one-way slabs. Okay, it's a very good, useful resource. I recommend you read all of this article 5-2, but I will just focus on the part that I'm working on right now. So this is the model we can use if you are working with a beam, permissible analysis model for continuous beam subjected to only gravity loading. If it is supported by columns, you can use this type of model. But if it is supported by beams, your beam or your slab is supported on the beams, then this is the better approach. Okay, that you use this model, and then you do a little bit of modification at the end. I'll tell you what modification needs to be done at the end. Okay, so let's start developing the model. I'm going to use software, freely available software, Research to the Educational. So this is the member with, this is the cross-section, the cross-sectional properties of the member and the material property. So let's start drawing the member now from 0, 0 until this second node. Make sure you don't, you keep looking at this place when you're hovering over a node. Let me restart this. So start from 0, and then click at 6.75 point, not the next point. Okay, click at 6.75 point. And then you go to 20.75, and then 34.75, and then 48.75, and 62.75, and then 76.75. Okay, so there we are. We have drawn the members, and then you need to define the boundary conditions. So let's start defining the boundary conditions. We will insert rollers at all these locations except the last one. We will insert the hinge. So starting with a roller, we'll start here. Okay, roller, and then for the last one we'll use the hinge or the pin support. Okay, this is just a conventional procedure where we have at least one support capable of resisting the horizontal load, although horizontal load is absent in this case. All right, so I think we can no more need to keep looking at the grid lines. So we will just stop looking at the grid lines, okay? And now next we need to apply the loads. Now, we'll do the analysis several times, starting with dead load, which will be applied throughout all of the spans, because the dead loads will exist in all those cases. So starting with the dead loads will be, okay, so let's start with a distributed, maybe we can start one here. So direction is y, and then starting magnitude would be, you can see the dead load intensity that we have calculated is, the effective dead load is 123 psf. Now this is pound per square foot, and since the tributary width is just 1 foot, so 123 pound per square foot multiplied by 1 foot will give us 123 pounds per foot, or we can say 0.123 kips per foot. Okay, so this is minus 0.123. Minus is because we want to apply downward, and then the next would be starting location is 0 and then ending is 6.75. Apply. Okay, and then we can say the next members. So this is in fact, what is this 14? The starting location, this is for the member. For this member, if you say the starting location is 0 and the ending location is 14, it means that the UDL will start from this and this end of the member to this end of the member because it is 14 feet long member. So these are actually these 0 and 14, these are the local coordinates of the member. Okay, apply. All right, so all the members subjected to the dead load. Okay, and then you can just start doing the running the analysis. Okay, and then you can get the member forces. Okay, you can, if you want to see, you can see the bending moment diagram over here, but we will be extracting the results because we need to process them. Okay, so these are the results. All right, so by default, this will give you the results for 5 sections in each member. Now, what does that mean? It means that the section 1 and the section 5, the total 5 sections, well, you can modify this thing in the settings if you want. You can go to this, and we need to in fact change this, but I want to show you what happens if you use just 5 sections. Okay, so what does this 5 section mean? It means the first and the fifth, these are the starting and the ending of the members. Okay, so this section for this member M1, okay, this for member M1, we better call change the names of these members from maybe M1, M2. We could just give them more meaningful names. Maybe we could say we need to, I think, modify these names over here. Let's first change the names. This may be called as M1, but we're going to call this one member as AB, the second one as BC, and then CD, okay, and then DE, and then EF. Okay, these are better names compatible with our calculation. These are just names, but we'll be able to get better understanding. This one is still called as M1, the cantilever. Okay, so now coming back to the analysis part, we'll have to rerun it because we changed the names. Okay, so member forces, there you are. Now these are the names now. So so 1 and 5, these are the starting and the ending sections. I wanted to tell you that we need to modify this from 5. We need to have more than 5 sections. So the results will be available for the locations or sections only. If we have 5 sections, it means we are dividing the span in 4 parts, L by 4. For each L by 4 location, we will have the results available, results for the axial shear and bending moment. We want to increase these points because we want to make it a little more, we want to make the diagram a little more smooth. Okay, so the maximum that we can go is, let me show you, the maximum that the RISA is allowing me to go is 10. But 10 is not a great number. Reason, because if you have 10 sections, it means you're dividing your beam in 9 equal parts. Okay, so 9 equal parts. Then it means that you will not be getting the results directly for the mid span, because 4 by 9 and 5 by 9, there is no, so half of 9 is 4.5, and you will have iterated for section the 4th and the 5th locations. You will not be getting directly the results for mid span. So I better reduce it to 9. In this case, I'm dividing it to the beam in 8 equal. Each member will be divided into 8 equal parts. So that way you will be getting directly the results for the mid span. Okay. So let's let it change. Okay. And then rerun the results. So now you can get the result for the 9 different parts. For all these sections, 9 different sections. So we will just copy this, okay, and paste them here, okay. And I want to give names to what these locations are. So I would rather say, Control C, just one location is enough. So this is the member. Okay, this is the member, and this is the section number, and what else? This was the axial force. Okay, axial force in Gibbs.